Welcome back. It's time to answer the question, which element's radioactive decay has been used as a power source in space missions such as the NASA Galileo launch? The correct answer is plutonium-238. I have shown you how to calculate rates and orders of a reaction using the integrated forms of rate laws. So, are you ready to solve some numerical problems with me? Here is a typical question that examiners could ask. The decomposition of dinitrogen pentoxide to nitrogen dioxide and oxygen is first order with a rate constant of 4.8 into 10 raised to power minus 4 per second. If the initial concentration of dinitrogen pentoxide is 1.65 into 10 raised to power minus 2 moles per liter, what is the concentration of dinitrogen pentoxide after 825 seconds? Now for a first order reaction, the integrated rate equation is given by equation 1. We know that the initial concentration of dinitrogen pentoxide is 1.65 into 10 raised to power minus 2 moles per liter. The rate constant K is equal to 4.8 into 10 raised to power minus 4 per second. We also have the value for time as t is equal to 825 seconds. Substituting the given values in equation 1 gives us the concentration of the reactant as 0.0111 moles per liter. So far, we have been discussing solid and liquid reactants. But what about gaseous reactants? As you must know, the concentration of gaseous reactants is expressed in terms of partial pressure. So let's see the integrated rate equation for a first order gaseous reaction, which has been represented as equation 1. Let the unit of pressure be atmosphere. So when T is equal to 0 and the reaction has not yet begun, we denote the initial pressure as Pi atmospheres. As the reaction progresses, let the total pressure at time t be Pt, which represents the sum of the partial pressures of A, B and C respectively. We can write this as Pa, Pb and Pc. If X atmosphere is the decrease in partial pressure of A at time t and 1 mole each of B and C is formed, then the increase in partial pressure of B and C will also be X atmosphere each. So we get Pa, Pb, Pc in terms of X as 1A, 1B and 1C. Using the rate equation given by equation 2, we get equation 3 since the concentration is expressed in terms of partial pressure. Now let's calculate Pa. Total pressure is given by equation 4, which on rearrangement gives equation 5. Using the value of Pa from equation 6 in equation 3, we get the integrated rate equation for a first order reaction with gaseous reactants. Do remember that although the two calculations we discussed for gaseous and non-gaseous reactants seem different, they follow the same basic principles. So keep thinking of the concepts behind the chemistry and you will never go wrong. Speaking of basic concepts, next I want to talk about a very important idea in chemical kinetics that forms the basis for many applications in the fields of medicine and radioactivity. I am talking about half-life, which is defined as the time in which the concentration of a reactant is reduced to half its initial concentration. It is expressed as T half. The study of half-life is used in the diverse field of toxicology, carbon dating in archaeology, and even in forensic science. For a zero-order reaction, half-life is obtained by writing the concentration of the reactant as half of its initial concentration. This gives equation 2. Thus, T half is directly proportional to initial concentration of reactant and inversely proportional to the rate constant. I am sure you can now confidently derive the half-life for a first-order reaction. It is obtained by denoting the concentration of reactant as half of its initial concentration. This gives us equation 3 as the half-life of a first-order reaction. Note that T half is independent of concentration of reactant. Take a look at this reaction and then think back to that plastic plant I found in my garden. The two have a lot in common. At first glance, this seems to be a first-order reaction, but its experimentally determined rate law proves otherwise. Intriguing, isn't it? Well, this is because of the excessive concentration of water involved in the reaction. Since this excess does not vary much with time, it is not taken into consideration when writing the rate law. So even though there are two reactants involved, the reaction behaves like a first-order reaction. Such reactions, which seem to resemble first-order reactions in spite of having two or more reactants, are called pseudo-first-order reactions. Time now to take a very real question from our student.
I have noticed that some exam questions gives you a graph of half-life versus initial concentration and ask you to predict the order of that reaction. But by looking at the graph, how can we predict that?
I'm always delighted when students bring me such interesting questions. As you have just learned, half-life is the time in which the concentration of a reactant is reduced to half its initial concentration. For a zero-order reaction, half-life is directly proportional to the initial concentration of the reactant and inversely proportional to the rate constant. So, if the concentration increases, the half-life also increases. This means that the graph of half-life versus concentration should be a straight line with its slope passing through zero. Now, for a first-order reaction, the half-life is independent of the initial concentration of reactant. So, the graph should be a straight line with the half-life remaining constant for any change in concentration of the reactant. Well, gauging the half-life of this discussion, I think it's time for another break. But return quickly because you don't want to miss Exam Decoded.